This is a guided reading for Chapter 25. If you would please get out your books and turn to Chapter 25, page 751. Once there, take a look at the upper right, and I'm going to explain that with another analogy for you. They have in the middle there a pulsating sphere with the wave fronts moving out, and then they draw a line perpendicular to the wave front, and they call that the ray. That's very similar to you looking down to a pond and dropping a pebble. If you drop the pebble in the pond, you see the waves go out in all directions. If you put an arrow on the top of one of those waves in the direction it's traveling, you'll get your ray. We'll use the ray model to describe a lot of things in light. So we'll use the ray model for our optics, for our lenses and our mirrors. So when you're seeing that line in all the problems, the rays, it really represents one of those wave fronts moving in that direction. If you take a look at the bottom right of page 751, figure 25.3, you will see our first application of the ray model, and that is when a light ray comes in and hits a smooth surface, it bounces out, or not even smooth, doesn't matter. Light ray comes in, hits a surface, whatever angle it hit at, it bounces back out at. Or, more accurately, the angle of incidence, the angle it hits at, is equal to the angle of reflection. Theta I equals theta R. If you take a look at the picture, just so you know how they measure theta, it's relative to a normal to the surface. Okay? So it's the angle between the perpendicular to the surface and whatever the light ray came in at versus what it came out at. So angle of incidence equals angle of reflection. Go ahead and turn to page 752, the next page. At the top there, you'll see two different types of reflection. One of them is called specular reflection. Think specular smooth. The other is diffuse reflection. Specular reflection would be objects you could see yourself in. So spoons, glass, polished metal, mirrors, any of those things could be specular reflection. The idea is that you get the light rays coming in parallel to each other. They're going to go out no matter where they hit, still parallel to each other. So in the specular reflection is a nice pattern. One line comes in parallel to the other, and that's the same case for going out because the surface is smooth compared to the wavelength. If you look at figure B at the top of page 752, the diffuse reflection, you'll notice that when it comes in, it still follows theta I equals theta R, but because the surface is changing relative to the wavelength, it's changing enough that when they come in parallel, they certainly don't all go out parallel. It's a mess. Objects that would be diffuse reflection would be anything you can't really see yourself in. So your clothes, your desk, most floors, a piece of wood, anything like that would be an example of diffuse reflection. Take a look at section 25.3 towards the bottom of that page, the formation of images by a plane mirror. This is our first type of mirror and the simplest type of mirror. This is the one you're most familiar with in your bathroom or in your house, the flat surface mirror. There's no curvature to it, or very, very little. For the formation of images on a plane mirror, it's pretty simple, and I think you'll remember these because you've been looking at them all your life. The image is upright. The image is the same size as you are, and the image is located as far behind the mirror as you are in front of it. In other words, you stand 3 feet from the mirror and you're 6 feet tall. Your image looks like it's 3 feet behind the mirror and 6 feet tall. And it's upright. It doesn't flip. The mathematical reasons for that we're going to take a look at. On the top right of page 753, if you take a look at figure A and figure B, this will help us figure out where the image is going to be. First of all, as a reminder, you'll see the chess piece there. For you to be able to see something, light from that object or a light ray from that object actually has to hit your eyeball. So it comes out of the object, bounces off the mirror, and comes up to your eye. If you trace that back through the mirror to where the image would appear, the angle that hit your eye, your brain says, oh, it looks like it's behind the mirror. Now, no light is actually passing through mirrors, so it is a virtual image. If you go behind a mirror, there's no person standing there or no chess piece actually there. Okay, you can put a screen there, and you will not get an image. By a screen, I mean like a movie screen or a piece of paper. You're not actually going to see something if you put it back there because no light passed through the mirror. On the bottom, to the right side of page 753, figure 25.7 is the setup for the mathematical proof of this. Just to make sure we're set on plane mirrors, go ahead and read all of 25.3 until you get to conceptual example 1. If you have questions on how they proved where the image was, please ask me before or after class or even during class. After you've done that, come on back. And now what I'd like you to do in section 25.3 is take a look at conceptual example 1 and conceptual example 2. Read through those, spend some time, make sure you believe what they're saying and can follow it. If you can't, I would recommend going back and reading section 25.1 and 25.2. If you can, great. You don't need to read 25.1 and 25.2. All right. So some of you have read 25.1 and 25.2 because the conceptual examples weren't so hot. Others are ready to keep going. Let's take a look at, and everybody will need to keep going, let's take a look at 25.4 on page 755, spherical mirrors. On page 755, section 25.4, you'll see the picture of a spherical mirror about halfway down the page, the big sphere. If you cut out a portion of that sphere and pull it out, you're going to get a concave or convex mirror, depending on which side you make reflective. So picture a sphere, for this first example, with a reflective coating on the inside. If you cut out a chunk, you're going to get a concave mirror, much like you see in the front right of the room, or for a convex mirror, the front left of the room above the board. For a concave mirror, a light ray before I explain that, for concave and convex mirrors, you could measure the distance from the center of that imaginary sphere to the mirror. That distance, labeled right next to it as R, is the radius of curvature. So you'll see the radius of curvature for a concave and the radius of curvature for a convex mirror. At that point you measure over R, we'll put C, the center of curvature. So in the picture of the big sphere, that's where the center of the sphere would be. You'll notice for a concave mirror, it's to the left. For a convex mirror, it's to the right, okay, because of where the sphere would exist. All right. Take a look at page 756, and this is one of the first things you've got to realize for concave and convex mirrors, that a light ray that comes in parallel to the principal axis will strike the mirror and come out through the focal point. There's also the talk of spherical aberration in this section for near the edges where that doesn't happen. Okay, it doesn't happen perfectly. If you had a parabolic mirror, they would all go through the focal point. So a sphere is not perfect. So that's the spherical aberration part. You also notice the focal length of a concave mirror, equation 25.1, is 1/2 the radius. So if you go half the distance from the center of curvature, you get the focal point. All right. Everybody actually needs to read 25.4, so go ahead and do that. I've hit some of the highlights. One other highlight is to notice that on page 757, the focal point for a convex mirror is on the other side of the mirror. And the radius of curvature, the focal length is -1/2 the radius of curvature because it's on the other side of the mirror. As you're reading, just pay careful attention to their discussions on where everything is located and how they're drawing the rays. And then come on back. Welcome back. Section 25.5. Some of you really need to read this, some of you don't. So if you haven't done ray tracing in a while, you absolutely must read everything in here. For those of you that remember ray tracing and were good at it, I'm going to give some highlights that everybody can listen to. But remember, if this is an area where you haven't done it in a while or you were weak, make sure you read all this. On page 758, you'll see the ray tracing for a concave mirror to get 3 rays drawn. You have one come in parallel, go through the focal, one comes in the focal comes out parallel, and then the one that comes through the center of curvature. All 3 of those rules have examples in 25.18 If you can follow the example or figure 25.18 and you're okay with all the pictures on how they got where all the images formed and whether or not they were upright or upside down and all that stuff on page 758, 759, you're okay on concave mirrors and you don't need to read in between. Convex mirrors start on page 760, and you'll see, so turn to page 760, you'll see the 3 strategies for getting 3 rays for convex mirrors. You don't always need to draw all 3, but you at least need to draw 2.
Justin Walters, please report.
To draw those, follow the instructions and take a look at figure 25.22a at the bottom of the page for a convex mirror. There's one example. If you're okay with how they got that for the image, you can skip 25.5. In 25.6, so those of you that need to read 24.5, please do so at this time. And I'll be helping some of you out with ray tracing examples in class. 25.6, everyone needs to read. When you're reading it, pay careful attention to the signs. This is the most common mistakes I see on mirrors is you mess up your signs or you don't know what the signs mean. So please, everybody, carefully read through 25.6, including all of the pictures and all of the example problems. So spend a good half an hour looking at, probably a good half an hour looking at 25.6. After you're done reading 25.6, 25.7 includes 2 more examples. Please read those as well. It'll help you significantly on the homework. You should be familiar with those examples before you come and ask me for help with the homework. After finishing all your reading, your problems are on the blog or they are on the board. Attempt those and be prepared with questions on the reading and the homework on Monday. That will be the only time we spend on mirrors. We're going to be moving on to lenses Monday and be done with optics by Tuesday. So it's really important that you're actually doing these problems in a timely manner.